Hello, in this video we are going to perform some physics experiments on a homemade incubator. What we see here is a homemade incubator and its controls. Let's dive right in and look into this incubator. Here we see the insides of the incubator. An incubator is used to hatch eggs. Right now we have 20 chicken eggs inside. Right, so that those eggs are laid out. Let's look at the components of the incubator. What we see here is a heat sensor. It's a temperature sensor. It's a fairly accurate digital temperature sensor. Over here we have a humidity sensor plus a temperature sensor. This detects both the humidity and the temperature, but this is not accurate as the other one. Here we have a fan, and that's a rotating fan that's used to circulate air within the incubator. We have an incandescent bulb, and then we have a bowl of water. A bowl of water is used so that the humidity or inside this can be increased to match the humidity of a chicken. So here the principle of an incubator is that the temperature that needs to be maintained in the incubator should be the same temperature as that of a chicken. Here we have a small vent hole that's used to exchange air from the outside. The eggs are very much a living being, and hence the growing chicks needs oxygen and they expel carbon dioxide. So if there is no air circulation, the chicks are going to die of not getting breath. The basic idea of the incubator is that when the temperature sensed goes low, the lamp turns on and that heats things up as well as it evaporates the water. When the temperature goes above a certain level, the bulb automatically turns off, and then that way the temperature inside is maintained at a constant rate. I have turned off the bulb. Now I am turning on the bulb, and as you can see that the bulb is on and it's trying to increase the temperature. That's the fundamentals of an incubator. And now let's look into how the temperature and the humidity looks like inside an incubator. Here we can see the output of those various sensors. The first measurement is for this digital sensor. Here we can see that an average temperature of 37.5 degree is maintained. When the temperature goes up, the incandescent bulb is turned off, and when the temperature goes down, the bulb is turned on, effectively maintaining an average temperature of about 37.5 degrees. 37.5 degree is the temperature of humans, and it's also the temperature of chickens. And so that's the optimal temperature that it should be for an incubator. So this is over a few hours of measurement. This is the second temperature sensor that is within the humidifier itself. This is not as accurate as the first one. So here we see fairly big steps. So this is 38 degrees and this is 39 degrees. And this is not as accurate as the other one. But nevertheless, we can see an average temperature of about 38 degrees here. Here we see the humidity. The humidity is not constant. This is measuring the relative humidity. So the relative humidity goes from 53 degrees down to about 49 degrees. The reason why the relative humidity comes down is due to the shape of the vessel that holds the water. It's got a larger surface area on the top, and it's got a lower surface area in the bottom. So the area that's exposed to air comes down when the water level comes down. And additionally, the distance between the incandescent bulb and the water level increases. So therefore, when the water level comes down due to evaporation, there's less and less evaporation, and that's the reason why the relative humidity comes down, even though the temperature remains more or less the same. In an incubator, it is important to maintain the relative humidity for the healthy growth of chicken. The first experiment we are we are going to perform is to turn off power to the incubator. Even though we have live eggs inside, it is perfectly okay for the power to go for some duration. And that's because in nature, the chicken leaves the hatching area and for food. So the eggs are exposed and the temperature of the eggs actually comes down for some time in nature, and hence it's okay for the power to go. So we're going to disconnect the power, and that turns off everything, and then we are going to leave it like this for a few minutes, and then let's observe the temperature and the humidity. It's now about half an hour, and we are going to turn on the incubator and then let the incubator heat back up to 37.5 degrees. So I've turned on the incubator. As soon as this comes up, the incandescent bulb should turn on, and it will remain on for some time. Now let's see how the graphs look like. Let's now examine the graphs for the experiment that we just conducted. The small blip here is a small test that I did before I actually turned it on. So I had turned it on for a brief period and turned it off. So that let's ignore this small blip. This is the graph that's interesting. So you can see that the temperature did come down when the incubator was turned off, and then the temperature rose up fairly quickly after the incubator was turned on. If we look at this graph, you find that this graph is not a straight line. In fact, the drop here is faster than the drop here. And the reason for that is that the heat exchanged is a function of the temperature difference. Here, the incubator is at around 37.5 degrees, whereas the outside temperature is lower than 32. So when the incubator is at 37, the heat difference between the outside temperature is higher. Consequently, the drop is faster. We say that the slope is higher here. And then when the temperature has already come down, the heat difference between this new low temperature and the outside is lower. So since the heat difference is lower, the drop is not as fast. So that's the reason for this peculiar shape that we see in temperature. Whereas here we have turned on the incubator. This is pretty much a straight line. We don't see this type of two slopes or different rates here. And the reason is because the incandescent bulb gives out a constant heat depending on the wattage of the bulb. So that's why, since the heat delivered is constant and the temperature difference does not matter much, we see a fairly straight line here for the heat increase, and at which point the temperature went above the threshold. So the controller brought the temperature constant at 37.5. So that's the reason why we see this graph. Here we see the humidity graph. The small blip is when I had turned off the incubator for a short period and turned it on before the actual test. And here, this is the interesting graph for the humidity. Here we see that the humidity is increasing. The reason is because the humidity sensor is measuring the relative humidity, not the absolute humidity. So when the temperature drops, the relative humidity increases even though the absolute humidity remains the same. That means that at higher temperatures, air can take in more water vapor. So in this case, when the temperature was low, the relative humidity is 65. 100% humidity corresponds to the maximum humidity that water can take. So the margin between 65 and 100 is smaller than the margin between 54. So at higher temperatures, the water can take in almost the same humidity. So the humidity can double when the temperature was high, whereas when the temperature is low, it can only take in a little bit more. So the absolute humidity remained pretty much the same, whereas the relative humidity increased due to the temperature drop. If the temperature had dropped significantly, the relative humidity will come to 100%. And then if the temperature is dropped even further, water will start to condensate and we would actually see dew drops on the egg. When the temperature was turned on, we see that the relative humidity uh, was brought up fairly quickly, even though the absolute humidity did remain the same. For the absolute humidity to increase, more water needs to be vaporized. So we need to probably fill that container with water. So those are the interesting graphs that we see from this experiment. We'll do more experiments. The next experiment we are going to do is to turn off the fan. So here is the power to the fan, and I'm going to pull out this lead. So the fan is essentially turned off at this point. Let's see what happens when the fan is turned off. We'll wait for the graphs to settle. We'll review the graph and then we'll see the inside. This temperature is the temperature for the digital thermometer. This is the one that we use to control the lamp. Here we can see that that temperature doesn't change much at all. It maintains the temperature at about 37.5. This is the temperature measured at the humidity sensor, which is also a temperature sensor. Here we can see that the temperature, which was about 37 or 38, did increase all the way to 40 degrees Celsius. So the temperature did increase. So there's a gradient of temperature between these two. And here is the humidity. So here we can see that the humidity did decrease. Let's open the incubator and let's understand why this is the case. Here the fan is turned off. The blades are not rotating. This is the humidity sensor plus the temperature 2 sensor. This is the first temperature sensor. This is the sensor that controls the light. So the 37.5 degrees measured here. And this is the other sensor that is just used for reference. So what we saw is that the temperature there remained constant at 37.5. Yes, because that's what this controller is supposed to do. Whereas the temperature here increased. The reason for the temperature increase is because there is no convection. So there is still conduction. We know that there are three forms of temperature exchange: conduction, convection, and radiation. Convection is a forced air circulation, and so there is no convection. And in air, convection has the maximum effect. So there is no convection, and due to that there is a temperature gradient. There's a temperature difference between the bulb and the sensor, and that's why this recorded a higher temperature than this. However, when this fan was turned on, there was convection and the temperature remained the same throughout. The other effect that we saw was the humidity had decreased. The reason for humidity decrease is because the humid air from here does not get circulated to the rest of the eggs. So the humidity at rest of the incubator will drop if the fan is turned off. So essentially, turning off the fan had two effects. There was a temperature difference across the eggs and the humidity dropped. Temperature difference is not very good. These eggs will cook if the temperature difference maintains. So we need to turn this fan on fairly quickly. And here I am going to turn on the fan. The fan is now on. In this experiment, we are going to fill water to the container. More water. And now we'll see the effects of humidity when the water level is increased.
Here we see the long-term effect of the humidity coming down. So as you recollect, we ran this over a long time. We filled the water and left it like this, and we saw that we see that the humidity is coming down. The reason for humidity to come down is twofold. One, as the water level in the container comes down, the area exposed to air decreases because of the shape of the container. And then the distance between the top of the water level and the lamp increases, thereby reducing the heat that comes to water. So these two effects together will reduce the uh, humidity. So here we can see that the humidity is coming down. Uh, Ignore this blip, I'll explain that shortly. And then the humidity comes down, at which point the humidity now very rapidly drops. The reason for this very rapid drop is because the container eventually dried up, was completely empty, and then there is no more water to evaporate, and then the humidity did drop. This blip is because I had to open the incubator in between for turning the eggs. The eggs do require turning so that the embryo does not stick to one side. So I had to open the incubator. So you can see that the temperature did drop when I opened the incubator. So that's the effect that I see. I think this blip was probably a power failure. And so when the uh, power failed to the lamp, the humidity did increase. So that's the reason for this humidity increase and this temperature dip. Whereas when I opened the incubator, the temperature dropped as well as the humidity dropped. So our next experiment will be to see what happens when you actually open the incubator.
In this experiment, we are going to open the incubator and leave it like that for a few minutes, and let's see what happens. Yes, I'm going to open this incubator. And I'm going to take off the insulation. And then leave it opened. What we immediately see is that this lamp is now on and will remain on, and that's because the temperature has dropped. The sensor has detected that the temperature is low, and it's turning on the lamp to in an attempt to keep the temperature high. Now let's monitor what happens to the temperature and humidity after we have left this incubator open for a few minutes.
Yeah, the temperature was steady at 37.5. We opened the incubator, and then you can see that the temperature abruptly dropped from 37 to 32. So it's a drop of 5 degrees immediately. This happened to both the temperature sensors, and then we can also see that the humidity abruptly dropped. There's a lot of water vapor content inside, but when we opened it, the water immediately left the incubator, and consequently the humidity dropped. That's also a significant drop, 52 to 46. The effect is exactly the opposite. If we had turned off the incubator, if we had turned off the incubator, we would see the temperature come down, but we would see the humidity, the relative humidity, which we have already covered.
I hope that you did like these experiments with the incubator. It'll probably take a few more days before these chicks start to come out, and I'll try to put a video of these happy chicks after they hatch.